Now let's see how we can use the idea of Cramer's rule to find the inverse of a matrix, or to find a formula for the inverse of a matrix A. Let's start with the 2 by 2 example. So our matrix A, and we can do this in general terms. So our matrix A is 2 by 2, has components A, B, C, D. Now, what defines A inverse? Assuming here the determinant is non-zero, right? Assuming A actually has an inverse. Well, A times A inverse equals identity is the equation that defines the inverse for us. I could write A inverse A, but to use Cramer's rule, I actually need it in this format. So let's write A inverse with some unknowns. So let me write the first column as x1, x2, and the second column as y1, y2. And that's important. So I want to write this equation with matrices A, B, C, D times x1, x2, y1, y2 equals the identity, which is this matrix, right? So remember, we know A, B, C, D. We're trying to find x1, x2, y1, y2. Well, I can find the 4 components, x1, x2, y1, y2, through Cramer's rule, right? Because I can split this system. The way matrix multiplication works is that this matrix times this column is the first column in the answer, and the matrix A times the second column is the second column in the answer. So, in fact, maybe I should do something else here. Bear with me. I'll use a different color so we can visualize easier. x1, x2 corresponds to 1 there, and then y1, y2 corresponds to 1 here. So you say you have two systems of the form ax equals b, where b changes. So from Cramer's rule, what do we know? So if we look at the first system, right, we have a, b, c, d times x1, x2 equals 1, 0. How do we solve this system? Well, using Cramer's rule, we know x1 equals, I'm not going to be writing a, b, c, d all the time. Let me write just the determinant of a. I know that that's what is in the denominator, and I know exactly what the determinant of a is. I could write it here. It is a times d minus b times c. So that will always be in the denominator. The numerator is actually the determinant 1, 0, b, d, right? And that's very easy to compute. That's just d. So x1 is simply d over the determinant of a. What about x2? x2 will be, I'm going to have to put 1, 0 in the second column and a, c in the first column divided by the determinant of a. Now this determinant is actually negative c. You can use the formula, right? A times 0 is 0, minus 1 times c is c. You get negative c. So we have negative c over the determinant of a. We have found x1 and x2. Now I write the same thing for y1, y2. We have a, b, c, d times y1, y2. Now it is equal to 0, 1. So using Cramer's rule, y1 is equal to the determinant 0, 1, bd over the determinant of a. So that's equal to negative b over the determinant of a. And finally, y2 is AC 0, 1 over the determinant of A. That gives us A over the determinant of A. So you see, each of the components in A inverse are a ratio that has the determinant of A in the denominator. So actually I can factor that out. And what I get is a nice formula for A inverse, which is equal to 1 over the determinant of A times x1 has a d, x2 negative c, then y1 is negative b, and y2 is a. So we got ourselves a formula for the inverse of a 2 by 2 matrix, which only works, of course, if the determinant of A is not 0. Otherwise, you're dividing by 0, and that's not allowed. So, in fact, maybe I can remove the determinant of A here because we know exactly what that is. So the determinant of A is AD minus BC. And we're done. We have a formula for the inverse using Kramer's rule. Now the question is, how does this idea extend to a 3 by 3 matrix, 4 by 4 matrix, and so on? I think I want that in a box. All right, let's look at that. Now, the idea here, actually, I'm just going to give you the formula, and then we're going to explain why the formula works. So here is the formula for A inverse using cofactors. Remember these guys? We used them yesterday to find the determinant, to compute the determinant. In fact, if you come back here for a minute and you look at this matrix, by replacing 1, 0 instead of the first column, you can compute the determinant as this cofactor. The cofactor of 1, 1. Because you see x1 is in the 1, 1 position. So when you remove that in the matrix A, when you remove the 1, 1 position, you get that matrix D. The cofactor really is positive D because 1, 1 has a positive sign. So just the matrix will be a minor, but when you account for the sign and compute the determinant, you get the cofactor. So this D is the cofactor of 1, 1. Now, what about x2? Well, x2 actually appears to be the cofactor. So this would be, think of it as a 2, 1 position, and this is 1, 2 position. So it is the cofactor of 1, 2. The cofactor of 1, 2 will have a negative sign because 1 plus 2 is negative, and the determinant will simply be C. So that negative C is the cofactor of 1, 2, right? Then similarly, if we go for y1, so here is y1, it is in position 1, 2. The cofactor that corresponds to it, in this formula, of course, is the cofactor of 2, 1. The cofactor of 2, 1 is a negative b, because 2 plus 1 is an odd number. And then finally, for y2, the cofactor corresponds to the cofactor of 2, 2. So things are transposed, really, but you see that the cofactors come up. Now, in the general case, the formula is like this. You get that the inverse of a matrix A is given by 1 over the determinant of A. So the determinant of A is always there and comes from Kramer's rule, times the cofactor matrix transposed. Now, what is the cofactor matrix? Well, if you have the matrix A, So if your A is, say, I'll just do it for the 3 by 3 case. You have A11, A12, A13, A21, A22, A23, A31, A32, A33. Then the cofactor matrix is the matrix that you get by computing the cofactors for each of the components. So if I take the cofactor for 1, 1, obviously it will be a plus sign times the determinant of that minor. So that determinant will go in this position, right? So this will have the cofactors C11, C12, C13, C21, C22, C23, C31, C32, C33. Now, what's going on with, or how can we check this formula? Okay. By the way, I can use this formula to compute exactly one entry of the inverse of A. I don't have, like, let's say I only care about the 2, 3 position in A. The formula says that the ijth component, so ij means ith row, jth column. So the component of A inverse in the ith row and jth column is 1 over determinant of A times the cofactor that comes from the jth row and ith column. Okay, so that transpose means that the indices here are being flipped, and that's exactly what was happening in our example. So for 1, 1, well, you can change the order of 1, 1, you get the same thing. So for this diagonal term, the cofactor is just the cofactor of 1, 1. Same goes for the diagonal term of D. But for C, to compute x2, to compute the term in the 2, 1 position of the inverse, you actually look at the cofactor of 1, 2. Okay, and that cofactor happens to be negative C. And you'll see why that comes in the formula. So I can use this expression over here to find exactly one component of the inverse if that is what is important to me for some reason. Why does this formula work? So I can rewrite this expression. An equivalent way to write the formula would be, so let me multiply both sides by A. What I will get is the identity equals 1 over the determinant of A times, I could say A times C transpose, or I could say C transpose A. I will say A times C transpose. And then I can multiply both sides by the determinant of A. So that will give me an equivalent expression that says that A times the transpose of the cofactor matrix equals the determinant of A times the identity matrix. Okay, actually this formula is easier to demonstrate to be true. Whoops. Okay. So let's see why this formula is true. So again, I'll go with the matrix. I will represent the matrix. So I have A11, A12, A21. Sorry, A13. A21, A22, A23, A31, A32, A33. And now I have to write the cofactor matrix in a transposed form. So if I want to go 1, 1, 1, 2, 1, 3, I better write them in the columns. So I have C11, then C12, C13. So the C's correspond to C, not to C transpose, right? But I'm transposing them in this representation. So then I have C21, C22, C23, C31, C32, C33, and the claim, so I'm trying to check that this is true, right? The claim here is that what I get is the determinant of A along the diagonal, and everything else is 0. So first, let's check the diagonal terms. Where do they come from? Well, I don't know. Let's say we check this diagonal term. That is in the second row and second column. That comes from second row times second column. Now, this is where we see why we need to transpose the matrix. You see 2, 1, 2, 1, 2, 2, 2, 2, 2, 3, 2, 3. So if I look at the second row times the second column, or first row times first column, or third row times third column, actually any row times the corresponding column. So that's very important. What we get is, so first column, I have A11, C11, plus A12, C12, plus A13, C13. If I had not transposed the cofactor matrix, then I would not be having the same indices. But that's exactly what I want to have. And yesterday, when we talked about cofactors, we demonstrated that this sum gives us exactly the determinant of A. So this would correspond to expansion along the first row. Then if I look second row times second column, I will have A21, C21 plus A22, C22 plus A23, C23, and that again equals the determinant of A. So I can write, so this would be expansion along row 2. So any one of them gives me the determinant of A, and similarly for the third row times the third column. So the diagonal terms of this right-hand side matrix are clear. We know that they're going to be the determinant of A because that's exactly what the cofactor formula gives us for the determinant of A. It simply says that we can expand along any row, and then that formula gives us the determinant. The question here is, why is it that if I take, say, the first row with the second column, so first row times second column would be this term. Why is that term equal to 0? So why is it that when I take one row but the cofactors of another row, I get a 0? So why is it that A11 C21 plus A12 C22 plus A13 C23 equals 0? Okay, this is the big question. And we will address it right here. So why is this the case? Right. For a moment, forget about A11, A12, A13. Forget about, those are just some numbers, right? So let me write here maybe different letters. Maybe let me say alpha 1, C21, or let me just say alpha, okay, for a moment, plus beta C22 plus gamma C23, right? I want this linear combination. Well, where does it come from? It comes from a matrix. So I have to look at 2, 1, 2, 2, 2, 3. So I'm still working with a 3 by 3 matrix. And these components talk about expansion along the second row. Okay, so they say that in the second row, I should have alpha, beta, and gamma. Okay. Now, what's in the first row and what's in the third row? Well, those things have to be taken from the matrix A because that's what the cofactors are doing. We're looking at a linear combination. We're looking at the determinant. So this is the determinant of a new matrix can be interpreted, rather, as the determinant of a new matrix. So the question is, which is that matrix? So in this matrix, I know that the second row needs to be this alpha, beta, gamma, because this is expansion. This corresponds to expansion in the second row, provided that the components are alpha, beta, gamma. And then the first and the third rows are defined but by whatever is in the cofactors. But we know exactly what is in the cofactors 2, 1, 2, 2, 2, 3. To remind you, let me write the matrix A again. So we have A11, A12, A13, A21, A22, A23, A31, A32, A33. So now the cofactor, say C21. We get that by computing, so there will be a minus sign, but that's less important. The question is, what is the minor that it corresponds to? So I have to remove the second row and the first column. So now I see that in the first column, I should have A12, A13, A32, A33. So these things have to be in this matrix as well. Okay, well, let's write that. So I have A12, A13, A32, A33. So I have almost everything determined. What about the cofactor C22? I get that by removing the second row and the second column and computing determinants. So that says that the upper matrix better have A11 and A31 in there. What I'm trying to say is that these guys say that the first and third columns of A have to be in this matrix so that the computations could match. So I have here A11, A31. Now, if I try to compute the determinant of this matrix using expansion along the second row, this is exactly what I would get. I would get alpha times the corresponding cofactor, which is exactly C21, plus beta times the corresponding cofactor, which is exactly this. So they correspond to what is in the matrix A. And then gamma times this cofactor. Now, I go back to asking what is alpha, beta, and gamma. Now the values of alpha, beta, gamma actually matter. Well, they're equal to, so the first row is A11, A12, A13. The third row is A31, A32, A33. And now alpha is A11. Beta is A12. Gamma is A13. What do I see about this matrix? The first two rows are the same. So I know that the determinant here must be 0. And that's exactly what happens anytime you take a row that doesn't match the cofactors with the indices. You will always get 0 because it will correspond to two rows being equal or two columns being equal. And that's how we prove the formula for the determinant, for the inverse of a matrix. Now, maybe let's see one example on how to compute this in real life. Let's see if I have a nice matrix over here. I guess we could take this matrix A. We have 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1. Let's compute the inverse of this matrix. The determinant is simple, so we know that the determinant of A is just 1, so I don't have to worry about dividing by anything. The first thing I will want to compute is the cofactor matrix. Just so we don't get confused with transposition. I would say start with C. You can write C transpose as well at the end. So the first thing I'm going to do, and I will be erasing eventually, is I want to decide the signs that I need to put in here. So I will have plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. So each cofactor comes with a sign. By putting the signs, I will be reminding myself to pay attention. Now, what is the cofactor for this position? Well, I look for that position in in A. I remove that row and column, and then I look at the remaining determinant. So that we have the determinant of this smaller matrix that's again lower triangular. The determinant is 1. So actually, I replace this with a 1. Now I look for this position. I remove that row and that column. I see again I have that same matrix. That's again going to be a lower triangular matrix with determinant equal to 1. But because of that minus, I need to put a negative 1. So negative 1. And on the test, if you're working with a pencil and an eraser, this is nice. If you're not working with a pencil and an eraser, my suggestion would be write this matrix with pluses and minuses. You don't have to label it anything. And then right next to it, write your C matrix so that you'd never forget the signs. All right, going on to this term. So that comes from this position. And what I see is that the first two columns are equal. So I know that the determinant must be 0. So here I have a 0. Then I look at this position here. I mean, I could look at any position really arbitrarily. I could look at this position if I wanted to. I just have to match it. I remove this. I remove this. What do I get? I have 3 1s in the first term, 0, 1, 1, 0, 0, 1. So the determinant is 1. I have a plus, so I can just write a 1 there, right? By doing the signs, I really don't care. I can literally find all of the numbers in C in some random way. And in fact, why don't we do it? So let's find this position now. Well, I go to that position in A, I remove the corresponding column, the corresponding row, and what do I have? I have that these two columns are the same. So I know that the determinant there is 0. I better write a 0. All right, now I'm going to go back to doing these things in order. So here, if I remove that row and that column, I get two columns that are equal. So again, I get a 0. Then I'm going to go for this position. I remove that row and that column. These two columns are the same, or I get a row of zeros. Both tell me that the determinant is 0. Then I go to this position. I remove that column and that row. I just get a lower triangular matrix with 1s along the diagonal. So the determinant is a 1 with a plus. Then I go to this position here, removing the column, removing the row. The determinant again is 1, but I have a minus, so it should be negative 1. Then I go to that position, right? Removing the column and the row. What I get is two columns that are equal. And so I get 0 for that determinant. Then we go here, removing the column and the row. I get that these two columns are the same, and so I get 0 as well. So this over here is a 0. Then I go over here, removing that column and that row. I get a 1 for the determinant with a minus, so I have a -1 here. And the last row, we start here. Removing that row and that column, I get a column of zeros, so I know that the determinant is 0, or I get a row of zeros, same story. The determinant is 0. You can also say, well, you have zeros along the diagonal, and this is a lower triangular matrix. However you see it, the determinant is 0. Then we look for this determinant, remove that column and that row, we get a column of zeros, therefore the determinant is 0. Then we go for this position, removing the column and the row, we get a column of zeros, therefore the determinant is 0. And finally here, I know I have a plus. Removing that column and that row, I get determinant of 1. So this is the cofactor matrix. This is not the inverse. Now remember, the inverse of A is the transpose of the cofactor matrix over the determinant of A. Since the determinant of A is 1, I just need to transpose C and I will have my inverse matrix. So I have 1s along the diagonal. It just looks a little easier without all the zeros, easier to see. And the negative 1s right over here. And that's the way in which you can use the cofactor matrix. Now, let's say I gave you a matrix A and I said, compute for me. So I gave you this matrix and I said, find me A inverse 2, 3. So what I'm asking for is second row, third column. I'm asking for this number. How are you going to find that number? You can either use the formula, which is given right over here. And that's exactly what we'll do. The question is how to visualize these things, right? Or yes, you could just, perhaps the smart way is to just use the formula. So this is 1 over the determinant of A times the cofactor 3, 2. So if you write this, then things are easy. You have to compute the determinant of A. Okay, so the determinant of A is 1. And then you have to look for C23. C23 you get by removing the C32. Third row, second column. Okay, that's your C232, where you also have to pay attention to the sign. So you have to say -1 to the power 2 plus 3, or you have to write that matrix with signs. So up to you. You could either write the matrix that I had over here initially with the signs. In fact, you don't even have to go through all of them. You can start by doing this. You need to go to the third row. So we have plus, minus, plus. We are in the third row, but in the first position. And then we go into the second position, and that's exactly the one I want. So I have my minus. So either walk through the matrix to the position that you want starting at 1, 1, or use the formula -1 to the power of, well, I probably should write here 3 plus 2. It's the same thing, but not to get confused, because we were looking, and you see I made a mistake here as well. This should be 3, 2. I just didn't copy correctly. So third row, second column, I remove the corresponding row and column. And what I have is the determinant of what's left, which is 1, 1, 1, 0, 0, 1, 0, 0, 1. And this is exactly what I would like you to write for me. I would like you to say C32 equals -1 to the power of 3 plus 2 times that determinant, and then compute what that is. That is 0, and so A inverse in the 2, 3 position is 0. Okay, now that's not 23, that's 2, 3 position. Okay, that's enough for that video.